Hello, my name is Leonard Kleinrock. I'm chairman of the Computer Science Department at UCLA. We have here a really exciting and dynamic environment. And one of the activities that contributes to that environment and that excitement is the constant flow of visitors who come and spend time with us and interact with our faculty and student body. Each year, we select a few from among the very best researchers in the field and ask them to participate in our distinguished lecture series. The high point of their visit is the presentation of a lecture to our faculty and student body. And at that lecture, they present the state of the art in their field of specialty. They describe the research results, the open problems, and the directions in which the field is likely to go. And as you might expect, these lectures always generate a great deal of enthusiasm and interaction. I'm really pleased you have chosen to join us today. Let's go inside. The lecture's about to begin.
Welcome again. Welcome to the last of our distinguished lecture series this year. We've had a very eminent group of people, and we're going to end with a bang today. We have one of our own graduates from UCLA, David Nagel, and I want to tell you a few words about him. His father was the eldest son of a family of 12. His grandfather, quote, was not a particularly productive member of society, and I didn't ask him any more about that one. Okay? But the net result is that his father never attended school, even though he tried to tell people he attended all the way to first grade. At the age of 35, David discovered that his father was functionally illiterate. Could hardly read and could hardly write. And he managed to hide that fact from David for most of his life. But he was a very smart guy. He was a successful contractor in the building trades and then much more professional arenas. As a result, David did get a chance to play around with mechanical things, and his goal in life was to be an engineer. And I said, what kind of an engineer? And his answer was, there's only one kind of an engineer, a mechanical engineer. That's all that he knew as a youngster. And so his dad and mom did stress the importance of education. So again, that theme has run through essentially every one of the people I've introduced. No matter what the nature of their background, that educational stress was there. In fact, even though his father did not attend school, there was never any question but that David would pass through college. Again, that's a giant leap from a second immigration family. He lived in a rural area of Kentucky. He was almost condemned to go to a one-room schoolhouse for the first 8 grades, but his parents recognized that a public education would be better, and so he went to school in Louisville with his father commuting and dropping David off and picking him up each day. In the 6th grade, his elder brother went to school in Arizona, and therefore David also did his high school teaching there and studies there in a public school. All along the way, he was a top student. He recognized he had something special, but he was not among very challenging environment at that time. His elder brother was his role model. Again, there was a familial effect on the way in which he progressed. Then he came to UCLA for engineering. He was accepted at UCLA and at Stanford, but he was on a waiting list at Stanford, so he came to UCLA. And one of the things we had here at the time that David came was a unified engineering curriculum. There was no specialty in EE, CS, mechanical, aerospace. It was just one engineering curriculum. But he didn't know what he wanted to do, just be an engineer, if you will. One regret he has about our curriculum at that time is that he did not expose him enough to the liberal arts. And in fact, that's probably the case to this day. He was a terrific math student in high school, and he did terribly in math when he first came here. He was forced to choose engineering math as opposed to the mathematics as taught by mathematicians, and he found significant difference there. He had some memorable occasions here, some particular professors and some particular courses that he studied, but mostly it was some professors, most of whom are not here anymore, that influenced his way of thinking about education. People like Bob Elliott, some of you remember him, I'm sure. Peter Likens, magnificent guy, he's now president of Lehigh University, and a few others. He enjoyed especially a course in statistical thermodynamics, because that was the first time he realized that randomness could be put to effect in a fundamental way to explain things rather than to get in the way. He took a devastating course in engineering statistics. It was all calculations, no understanding, no theory. Again, an engineering abomination, unfortunately. He graduated with honors, and then he went to a graduate work here in biotechnology. And he worked with Professor Lyman and Gershon Weltman. Many of you don't remember that where Engineering 4 is now used to be a parking lot. But they didn't park cars there. They parked junk there. Old engineering equipment, big vessels and vats. There was a very tall columnar thing which they filled with water. And Gershon Weltman used to don his scuba gear and dive into this tank and study certain aspects of human behavior underwater. Well, David took the dive, okay? He went down and he studied, in particular, he recognized he had an inability to localize sounds underwater. You know, the speed of propagation in water is very much different than in air, and so it's confusing to a human. And so he decided to study that phenomenon. He felt he should be able to predict exactly how people perceived what they were listening to. He took a course, therefore, in perception in the psychology department. He got interested in that area, but he took his MS in engineering with some courses in psychology. Again, a kind of stress as to the things he likes versus the things he was forced to take in a fixed, rigid curriculum. The best thing was that Professor Lyman gave him a lot of flexibility to indeed explore other domains of interest rather than just pure engineering. Lyman was a very special kind of professor. He would attend many of the seminars of the students, and he was guaranteed to fall asleep. He was also guaranteed to wake up, and at the instant of wake up, ask a piercing question of whoever was talking. So he wasn't quite asleep. So when you find us faculty, occasionally dozing off, you know exactly what we're doing. Yeah, in the tradition that we should follow. He worked while a graduate, he worked for both Panoramic and Newman on aircraft noise. You know, BBN does more than just a fail at making computers. They also study acoustics. He got his PhD in the psychology department. Psychology department basically was the first department that had a mini computer that he could work on. So his first exposure to computing was in that domain. His thesis was on signal detectability theory in acoustics, 1972. And he took the traditional communication theory, detection theory, classical work, and applied it to the domain of acoustics. And a lot of it worked. But the piece that was missing was the human perception. And how do you, in fact, measure the way humans perceive things? It's not a very quantitative science. You can't ask somebody to give you a specific number as to what they saw, or I saw it sort of over there somewhere. Well, that doesn't lend itself to a quantitative kind of thing. So a lot of the science done then was deep interviews of small samples. And in fact, he did a deep study on a sample of 4 individuals, and discussed how they would listen in parallel to a number of things simultaneously. And 3 of his subjects demonstrated a great capability for doing parallel listening and perception, and one of them was purely serial. And they both behaved in the same way in this world. They could hear and understand and navigate. So his point is, it's not so much in the wiring, but in the strategy. Yet we still don't understand the way the brain works. And here's another example where the mysteries of the brain manifested themselves. After the PhD, he wanted what? More training. Okay? So he applied to be a postdoc at NASA. And his plan was to spend a couple of years there and go and teach someplace. Well, 17 years later, he was still at NASA. Point 1, you can't plan your career. And don't believe that if you step away from one thing, you can readily go back to something else. Okay? The steps you take tend to be rather important forks in the road as you move along. But the point about his career is that he followed his interests. He wanted to learn some more. He moved in a given direction. Didn't have rigidity about what he was going to study or where he was going to go. And in fact, he had support from his peer group as well as from his family in making those kinds of moves. At that time, NASA was a really exciting place. Okay? We had just a few years before put a man on the moon, which is an event almost as important as the ARPANET internet beginning here at UCLA that year. Okay? But it was important. It was a very free free-flowing place. He had lots of opportunity to study things in a variety of directions. And he considered himself a computer user, not a computer scientist. And that was true throughout his career. But at Ames, he built an automated laboratory with some competitors' equipment, Digital Equipment Corporation's equipment, and did research projects on sound perception, continuing in that same vein. He also studied how to make aircraft more quiet, or appear to be more quiet, so far as you were concerned as a human. His first 10 years, he contributed basically doing research in areas involving computer and perception. He got interested in human vision and found maybe the same principles of acoustic perception applied to vision perception, and he dropped acoustics and started studying vision. He worked on visual flight simulators. He was then asked by NASA to get involved with management. Now, this was a turning point in his career. They said, look, try a little bit. We can use your help. To manage a small simulation research facility. So still strong research, a little bit of management. And he helped get the facility approved at the government level. He spent dozens of visits to Washington, as he says, crawling around Congress, okay, convincing, and the FAA to convince people they should support this facility, and indeed he was successful. It was approved, so therefore his management skills were proven to the rest of the world. It was in those years that he did his last research, okay? As he says, in the wee hours of the morning, for 9 months straight, till he got too exhausted to squeeze that in, and basically gave himself to management, okay? He ended up heading a division in human factors regarding safety, command control, full spectrum of things, even involved in designing a spacesuit. All with computers as an aid in making those things happen. And then, as it happens, shortly after the Challenger blew up, NASA failure, he met some people at Apple. This was 1987. And they asked him if he wanted to do anything else, and he indicated, yeah, I might. So he went to a new planet called Apple, okay? A very different world. He started out, they asked him if he'd head up a group, and he had been heading up a group of 250 to 300 people with lots and lots of site visits. He had 80 program reviews that last year. That sort of convinced him he really didn't like that aspect of management. We just had a site visit today, by the way. That's like an in-joke. Nobody's laughing. So at that point he decided, it was a great site visit. He decided at that point NASA was not too exciting with all the site visits. He did decide to go to Apple. He started managing a group of about 20 people in advanced technology with a focus on graphics and sound applications and some AI. He did that for 1 year. Now watch the progress. It went to 120 people the next year. Then some guy who happened to be VP of the advanced technology group went off into the product division, and some other guy named Scully, who was CEO of Apple then, asked David to head the advanced technology group. It was now 250 people he was managing. He did that for 2 years. Then serendipity followed again. The fellow who headed all of the software for Apple went to Microsoft, okay? And Scully asked David to run the software group, which he did for 1.5 years. Scully's replacement, shortly thereafter, asked him to head up all of the hardware and software development at Apple, which he's now doing. Now, Apple is structured as follows. There's a CEO. That's number one. David's directly below him. And David controls all of the research, product development in hardware and software. The other people at that level, for example, is a senior vice president in marketing, senior vice president, manufacturing operations, and 3 guys who run sales. Okay? And they handle sales in various pieces of geographies. He's been there for 7 years. Meteoric rise in management after many years of research and research directing and engineering. He feels that all large organizations are bureaucracies with the same kinds of structure, and your skills in one map over to another. He was heavily influenced by a manager he worked for early on in his career who had the interesting credo that honesty and looking out for the success of the organization mattered. And it stayed with him and it's served him well. He wishes he had gotten a proper model of how to achieve success early on in his career. His model is, it takes 3 to 5 years to do anything successfully. And so how many 5-year intervals do you have in your life? Okay, in your professional career? If you're lucky, you have 7 to 10. So you got a chance to do 7 to 10 really successful things in your life. Okay? And you ought to count them off as you go along. Okay? We hope you do at least one biggie. Where did he learn to do management? He never took a course in management. You heard his career. The way he learned to do management is that he was teaching an extension course, where was it? In University of Redlands, on management. He'd been doing some stuff on high technology, operations research, and quantitative topics. And one day they asked him to teach him something on management. The only way he could learn was to learn himself and teach it. As we all know, as one day you'll all know, the best way to learn something is not to sit on that side of the podium, but on this side. Because you got to keep ahead of the people on that side, okay? And that means you got to learn it well. His message to you is as follows. Simply the message you follow himself. Follow your interest. Careers are hard to plan, and the randomness of nature creates opportunities for you. There's lots of success paths and strategies that work well. Choose one, but recognize it's not all plannable, as was not his. David, it's all yours. Tell us about the sea change in PCs. Thank you.
Dilettante seemed to come to mind. It sounds like I didn't know what the hell I was doing at any point in my career. Kleinrock's invitation to come down here was delivered very innocently, without the information that he was at some point going to sit me down in his office and elicit all of this terribly damaging information and replay it back to you. So if I had known that, I may have been a little more, may have bargained a little better. I do actually have a lot of wonderful memories about UCLA. I spent many hours in this very room. In fact, as I walked in, I had two memories. One, you mentioned Professor Likens. I took a course in mechanics from Peter Likens, and one of the things I remember most vividly was he was trying to describe to us, explain rotational moments of inertia, and got up. He had a little table that he always had in the middle of the lecture hall. He got up on the table on his back and was trying to behave as a cat would and show us how cats actually manage to manipulate themselves so they always land on their feet, which we were all, so it was a bizarre thing to do. None of us have ever seen a professor lying on his back in the middle of the office, so he was a very memorable teacher. The other was I took a course in operations research in this room. I won't say who that was because he was a bit of a crackpot, but he, in all honesty, he spent most of the time, he had worked for the RAND Corporation for many years, and he had spent most of his early career apparently designing very strange circular calculators which would allow him to compute the effectiveness of, for example, bombs and artillery shells in populated areas, and he would, with great pride, describe these things to us. We always thought that was a bit bizarre, particularly in the middle 60s. So anyway, the career at UCLA was very interesting. But none of that has to do anything with what I want to talk to you about today. What I'd like to do is to give you an overview of the personal computing industry, because I think it's at a very interesting jumping off point. The industry is fairly, it's less than a quarter of a century old at this point. Probably seems like a long time to a lot of you. It doesn't seem very long to me. But even at that age, it has already gone through several interesting phases. And I think that we're at the point at which we're about to make, or about to see made, a set of very interesting qualitative changes in the industry, which themselves can be traced back to the way the industry is structured on the one hand, and sort of the relentless march of technology on the other. So what I'd like to do is to give you leave you with a sense of what those changes are likely to be, try to indicate some directions for those changes, but along the way give you a sense of the way that the industry actually operates, because it's a very interesting industry. One of the things that I have found is that the dynamics of the industry are almost as interesting as the technology. It's a fascinating industry. I think it may be unique in American experience, or in the experience of people in the world, and the degree at which, and the rate at which it's grown, and the way at which technology has changed the career and changed the industry, and promises to continue to do that over the next couple of years in a very dramatic way. It is a very large industry. The overall computer industry, 40 to 50 years old, is a several $100 billion a year annual industry. The interesting thing that's happened in the last couple of years, of course, which is written about often in the newspapers and given the term digital convergence, is that the technologies underlying not only computing, but communications and even industries as diverse as entertainment are all now common, or will shortly be common. So the computing industry will exert an increasing influence over the entire economies, not only of the industrialized world, but I think increasingly of the non-industrialized nations, many of which are now rapidly developing, and in fact, in interesting ways, putting in infrastructure, which in some ways will develop much more fast than we even did in the West. So I'd like to go through that and give you a bit of a sense of history and talk about where I think that the personal computing industry is going. And then, as is the case with all Apple discussions, to show you a demonstration of some technologies at the end, which I hope will sort of illustrate where we are. So the industry that we think of as the personal computing industry, again, is something like maybe $100 billion, a bit more, $1 billion a year. The annual sales figures for related industries, particularly in the context of this digital convergence phenomenon, are also large. For example, catalog sales, you might be surprised to hear, is $70 billion a year. A lot of discussion now about interactive TV, interactive services. One of the chief of those is catalog sales, and it's quite clear that within the next, say, half decade or so, much of this $70 billion, which will probably itself grow, will be delivered over high-speed digital networks on some sort of a multimedia device, whether it's a personal computer or something else. Broadcast advertising, 27 million. Home video, 12 billion. Information services itself is actually a relatively old industry. It's almost $10 billion a year. Recorded music, 10 billion. Consumer electronics, which has grown both very fast and very non-profitably, is something like a $50 billion business. So you aggregate all these things, and you find out that underlying, in the next couple of years, all of these industries will be a digital technology that will probably propel something close to an industry which in the aggregate worldwide approaches $1 trillion. Now these industries already, in terms of international competitiveness, are extremely important in our economy. The entertainment industry alone, the U.S. entertainment industry, generates more than $6 billion a year in export revenues. It's actually number 4 in the list behind defense, agriculture, and aerospace. So what's happening today in digital convergence in the entertainment industry turns out to be, I think, very, very important for U.S. competitiveness and the U.S. economy because the U.S. is the center of entertainment, really worldwide. It's really driving the entertainment industry. But as large as all of these industries are today, one of the reasons I think that the computing industry continues to garner the attention of the public is because significant growth is still possible. So, for example, if you look at the penetration rates of the personal computer itself into different segments of the market, the K-12, higher education markets, it's barely 20%, or will be barely 20% in the next couple of years. Business it will only this year approach 50%. Now this is measured in terms of the total number of workers divided by the total number of PCs being used by workers, say in business, divided by the total number of workers. So roughly half the people in business now either use a personal computer or have one or use one occasionally. But that means that the other half don't, and so obviously that is a source of great future growth for the industry. Even more interesting is, particularly for a company like Apple, is that the growth rates in the rest of the world, including some very large markets like Japan, are actually, if anything, accelerating. Apple Computer last year sold $2 billion worth of computers in Japan. We grew from about, when I first went to Apple, I think we had 0.2% market share. We grew to about close to 25% market share in the 6 years since we started really selling computers there. But it's a wonderful market for us because it's growing at annual rates of 30%. As you can see, all these curves are actually turning up, whether in business. And again, the overall penetration rates are very small. So the industry is very important because as large as it's become, it has obvious significant potential, even ignoring some of these convergence phenomena that we talked about. Now, one of the things that I would like to do is to give you a sense of what it takes to be successful in this industry, because it is an incredibly competitive industry. Major companies who in one decade are not only successful, they are actually dominant. In the next decade, disappear. And this happens with a rapidity, I think, which is, again, if not unique to our industry, it certainly sets it apart from most other industries that certainly that I can think of. To give you a sense of how you can become successful in the industry, I thought I'd use a really simple diagram. Actually, there's a book that Charles Morris and Charlie Ferguson wrote called Computer Wars. I'm not sure if any of you have seen that, but they do the best job that I've seen in really describing what it takes to be very successful and, in fact, dominant in an industry. This is my homely attempt to, in a very simple way, describe the architecture of a personal computer. Hardware on the bottom, something we call an operating system. In fact, when the PC was first developed, this middleware layer that I showed here didn't really exist, and we really just had an application. One of the things that I think one of the great contributions of the personal computing industry to mankind was the concept of a platform. You know, prior to PCs being developed, when you wrote a piece of software, mini computers, for example, virtually all or much of the software development was custom development because the systems themselves changed so often that you really couldn't, few if anyone could make a living selling shrink-wrapped software because when the systems changed, nothing ever worked. The personal computer industry invented this concept of a platform, which was a combination of software and hardware specifications, an abstraction really, a hardware reference, a reference platform, which remained relatively stable. The specifications were published, therefore software developers could create applications which would not only run on the system sold at that time, but would continue to run. And in fact, it's become an absolute requirement to create systems which are backward compatible. So that old applications, I routinely show in some of my speeches an application that was created in 1984 that I can run on the latest Power Macintosh. Not all of them run, but that one does. I don't say the whole story, of course. So this idea of a platform became a very important element in the growth of the industry because it created and made possible the application software industry, which is today something like a $6 to $7 billion industry, depending on how you measure it. It's a very large and dynamic industry itself. Now, the interesting thing is how can you be successful in this industry? And the reason this diagram is important is that it illustrates or can be used to illustrate a principle of success. And the success principle is to control a layer in this diagram. And by controlling a layer, what I mean is have a dominant market share for some technology or product which corresponds to each of this layer. So that's one significant principle. Different people can control different layers. One of the interesting principles, if you control a layer on the bottom, it's relatively easier to control a layer above it because you get a time to market advantage. Let me give you a specific example. Today, Microsoft, one of the former lecturers who I think was here before me, Microsoft controls something like 85% of all the software sales corresponding to the layer that I've labeled operating system. Microsoft was able to get to that position by a whole series of both very clever and very systematic moves, largely by Bill Gates, but also with the complicity and help of other large companies like IBM, which came to regret some of the things that they did along the way to help Bill be successful. IBM also helped Intel, which controls about 90% of all the hardware that's sold in this industry. Now, the interesting thing about the ability to control a layer is that it gives, if you make products which correspond to the layer above it, it gives you potentially, theoretically of course, a time to market advantage. Because since your engineers know what you're going to do for the next version of the operating system, they can impart that understanding or actual information to the folks that are building applications on top of it, therefore gain a time to market advantage, and therefore end up through this time to market advantage, which is industry that moves as quickly as ours becomes absolutely preeminent. If you can gain a, say, a 3 to 6 months time to market advantage and you have a good product, you are guaranteed, virtually guaranteed, to end up #1 market share position, unless some major technology discontinuity or disconnect occurs. The thing that Microsoft has been absolutely masterful in doing is to exploit that principle to gain, first of all, domination, that is controlling market share in the operating system layer, and parlaying that into increasing market share position in the layers above it. So applications business, and to illustrate this point, Microsoft controls, of course, the operating system on Intel-based computers. They make applications, however, both for Intel-based and Macintosh computers, which we write the operating system. So they don't control the operating system on Macintosh. Their market share on the Windows application market, which is about 75% at this point of the total application market for application software, their share of the Windows application market is 50%, 51%, and growing at roughly 1 to 2% a year. So I think it's 51, 52% this year, probably going to 53 or 54 next year. On the Macintosh, where they make very similar sorts of applications, they have well less than 30% share at this point, and it's shrinking. It's going down every year. Now, you can't necessarily confuse causality with correlation, but in this case, it's quite clear that the application division of Microsoft does benefit from the fact that Microsoft also does the operating system. Microsoft has been able to do this in part, and I think has understood over the last few years and gotten quite sophisticated. And by the way, there's nothing inherently illegal. In fact, there's nothing not only inherent, there's nothing illegal in that. There's nothing that says that you cannot create a monopoly situation. There are increasing restrictions as you get closer to that point about exactly how you have to behave once you get to that position, but there's nothing wrong with it. And I have to say, Bill has been extremely good at developing this to a fine art. You can create, once you have a dominant position, in at least in even part of this layer, of course, you can also parlay that into greater and greater influence. For example, Microsoft has absolutely the controlling position in, for example, spreadsheets. They don't necessarily have controlling. They have a dominant position, but it's not absolutely dominant in the other components of a horizontal productivity suite, word processors, and so on. But what they have done to their competitors is to take the fact that they have the controlling share of spreadsheets, and by bundling all of their productivity applications into something called a suite and dropping the price so that it roughly is equivalent to what the other vendors charge for the individual components, they have in fact destroyed the market for people like Lotus, WordPerfect, and others. And Lotus, for example, is in the last year has become very clear will completely get out of the productivity software business as a result of losing market share, probably at the rate of 20 to 30% per year. So within a year or 2 years, unless something dramatically happens, it's quite clear that Lotus will be out of that business and will focus completely on their communication and collaboration products such as Notes. Once you have control on one platform, it turns out that you can parlay that control into another. Let me tell you how that works. Microsoft Office is now a product which most large corporations have standardized on worldwide as their horizontal productivity application set on Windows. When Macintosh salespeople go to those corporations, they say, well, we like your products, we like them to do multimedia or the other things that they're good at, but it's essential that you run Windows. Not that you're able to run Office, because that's how we send out all of our memos, that's how we do our financial information and so forth. So by having a control of it on the Windows side and having it become a standard, you de facto have to have it on your product. And if you do not have a version of Office which runs as well or as efficiently, you're significantly disadvantaged in the marketplace. So therefore, you can get fed back, find your market share position at the other levels of this little diagram, also in jeopardy. So it becomes a very interesting cycle. Interesting in this case, in quotes, of course. So the only thing that really, I think it's quite clear that this kind of the understanding of this dynamic in the industry was clearly responsible not only for the Justice Department challenging Microsoft's acquisition of the Intuit Corporation, but ultimately the success of that challenge, and even probably more significantly, the fact that so many people in the industry were willing to stand up and squawk about it to the Justice Department, both publicly and non-publicly, to keep that acquisition from taking place. Because it's very hard to see how to break this cycle of dominance of one layer converting into dominance of another layer, and so forth. And you end up with sort of a mental or an actual picture of one person controlling the entire industry. So the industry has actually begun to change. In the 1970s, of course, we had another dominant player, IBM, and everyone else was sort of an also-ran, ourselves as well as Microsoft. When Microsoft did the deal with IBM for MS-DOS, which they parlayed, of course, into control of this first layer, they were barely a $20 million a year company. They were a small number of people, and their capital was best measured in terms of intellectual capital and everything else. At the same time, IBM was a $36 billion a year company. Was a company that had a market capitalization or value of almost $40 billion, and Microsoft at that time was probably worth $10 million or $20 million. And yet they were able to unseat, over a period of barely a decade, what was once an unassailable opponent, competitor in the marketplace. When I was joined UCLA, IBM in the industry was the assumption. I mean, no one could do anything other than to make peripherals or to work around IBM's business model. In one decade, all that changed. And in fact, from the peak value of IBM, they lost 2/3 of the value of their company, most of which was converted to the value of Microsoft in less than half a decade. An absolutely astonishing change. Now, what made that possible? It was a change in technology which made it possible. IBM failed to recognize the importance of the microprocessor. They failed to recognize the ability of a change in technology to affect this massive change in the value distribution in the industry. And of course, they failed miserably to estimate the skills and the effectiveness of Bill Gates. So doing it. The IBM Corporation actually is still suffering, I think, internally and culturally from that change. They've been very successful with a new CEO in the last 6 or 9 months of regaining a lot of their market share. They're still about half of what they once were in terms of total capitalization, but they're in a way doing very well. But they've never really recovered from what Gates did to them in this revaluation of the industry. Now, other players have also, people who were very large, people like Ashton Tate and other people in the software industry who were once very large corporations, dominant corporations in their own right. Lotus with 123 was at one time an unquestioned spreadsheet leader. All of those companies now have either disappeared or have shrunk to the point at which their very existence is now questioned. How did that happen? It's pretty clear what happened to IBM. They basically lost control of this layer called operating system in their own industry. But how was Gates able to do it to people like Lotus? Well, again, with the complicity of IBM and an unwitting complicity of it, IBM and Microsoft announced, as you may recall, in the 1980s that OS/2 was the operating system of the future. It was very clear that DOS was a fairly relatively primitive piece of technology, and IBM, who's always been very interested and I think appropriately so in good computing architectures, went to work with Microsoft because it had a successful association with DOS, went to work on the development of the next generation operating system, OS/2, and they announced to the world that OS/2 would be their strategic target for operating system. Now, at some point, and there's varying accounts of exactly what happened, but at some point Gates became concerned about the viability of OS/2 commercially. Part of it was that Gates favored targeting the operating system on the 386 microprocessor, and IBM favored the 286 because of other economic considerations. And Gates was very concerned that OS/2 on a 286 would be a performance dog. So Gates began working on a layer product called Windows, a product which would sit on top of and provide some of the ease of use that he had already begun to appreciate was making the Macintosh successful. So he began to develop this product called Windows. And his own application developers began, most importantly, developing Windows applications, spreadsheets, word processors, and so on. At some point, Gates announced that OS/2 was no longer strategic to Microsoft and maybe still strategic to IBM. And in fact, they negotiated a sort of return of the technology to IBM, who continues to develop it to this day. But Gates put full energy on Windows and full energy on Windows applications. And in fact, he had already had such a dominant control of the operating system, the DOS layer, he was able to make Windows an incredible success commercially. And people like Ashton Tate went out of business completely. People like Lotus saw their market shares go from 80%, 70% down to 20% in a period of about 12 months. Again, a radical and dynamic shift. And the rest is somewhat, of course, I guess, is history. Microsoft is off and running. So in the 90s, this picture has changed quite significantly. And on the software side, Microsoft is absolutely the dominant figure and growing very rapidly. Companies like Lotus, Nobel, and even IBM, which has a very nice software business, are fighting like hell to maintain whatever positions they have and not lose more market share. Now, on the other side of the diagram, we have Intel. And Intel turns out to be a very similar story to Microsoft. Very successful, incredibly successful company. Again, helped by IBM. As you recall, IBM invested in them in the, I guess, the late 1980s for a time, and really got them through a major transition from a memory company to a microprocessor company. But Intel now is a similar situation in hardware that Microsoft finds itself in software. It owns 85, 90% market share worldwide for general purpose microprocessors. Now, the thing that Intel has done is they've taken a page from, I think, Bill's notebook, and they've begun to move up the food chain, move up this diagram. So hardware is a fairly, coarse term. There's microprocessors, and then there are systems built out of microprocessor and memory systems. Intel has a very nice hardware systems business. You may not know or may not appreciate that Intel this year will ship something like in excess of 10 million personal computers. It is the largest, in effect, personal computer manufacturer in existence. It creates motherboards, it creates the major logic boards, and ships those to companies, most of which you've never heard of. Small capitalization companies that sell locally, sell regionally, but there are thousands or hundreds of thousands of these companies, which are in effect not computer companies. Any three of us could actually start one of these companies this afternoon because you can buy all the components, the case, the motherboard, and everything else to build a personal computer. All I have to do is put our label on it and distribute it. So these companies are basically distribution companies. The distribution company financial model is, from a manufacturer's point of view like mine, not a very interesting one. It's a very, very low profit business because there's not much value added. All you're doing is basically moving boxes. So by creating a very, very efficient operation, which has basically reduced the ability, or in some cases eliminated the ability of people like HP and Packard Bell and others to differentiate their products, the value proposition for those companies has also been destroyed. So if you look at Compaq, for example, and look at what's happened to the stock price in the last 6 months, 9 months, you find this lost something like 25% of its value. The reason is that financial analysts who follow this industry can no longer see how Compaq can maintain the high profitability that it has enjoyed really since its inception. The companies that it's dealing with are operating at profit margins in the 2 to 3% range, in some cases less than 0, and Compaq has enjoyed 7, 8, 10% profitability based on revenues for, really historically since the company was in existence. So in effect, very similar things are happening both in the software industry and the hardware industry, and it's very difficult to think of anything that would fundamentally change that, because these companies have become very good at creating and maintaining these dominant positions. Now, I think that the thing that can change it, actually, is, again, the thing that enabled it in the first place. That is a major change in technology. The very thing that created or made possible the personal computing industry. There are various ways of looking at it. I talked about the importance of the platform in creating an industry that is, we now call this the shrink-wrap software industry. Another thing made possible the personal computer industry, and that is a microprocessor that was both cheap enough and fast enough to enable a fundamentally new way of having people interact with computers, the so-called graphical user interface. The same thing is again happening. Microprocessors have evolved to the point at which they're sufficiently faster than they were in the middle 1980s that the style of computing and what we can do with them is not only quantitatively different, it's qualitatively different. In the last couple of years, for example, the notion of a multimedia computer, that is a computer which is used primarily not for doing calculation or computation, but primarily for manipulating images, for manipulating and creating sounds and so forth and presenting them. That really wasn't, people talked about it 3 or 4 years ago, but it was really only the last year that it's become quite possible to bring that kind of performance to consumer price points. So the argument is that the microprocessor performance, the ability to build very, very dense memory systems, whether magnetic or semiconductor, has reached the point at which a quantitative improvement over the last few years is now a qualitative improvement. It enables us to make a qualitative change in a number of things, and in fact, to fundamentally change the whole idea, again, of what a computing platform is. This just happened to be some data. This is sort of 2 years. We're sort of here. These are different processors in the PowerPC family, which of course we use now to make Macintosh, Power Macintosh computers. And at the high end of the scale, you see that we're getting into the sort of half a billion instructions per second, useful instructions per second range within the next couple of years for a single chip computer. Now, at the end of this year, you will see multiple chip computers, microprocessors that have those kinds of performance capabilities, but again, those are very expensive. They're $1,500, $2,000 microprocessors. You can't make a $1,500 personal computer out of them. But in a couple of years, you will have that kind of microprocessor performance available at personal computer price points. By the end of the decade, without a lot of imagination, we're going to be measuring microprocessor performance more in terms of billions of instructions per second rather than millions of instructions per second. Now, at the same time, this chip family, the 603 chip family, turns out to be extremely cheap. That is, you can see prices for the microprocessor itself at the, say, 200 spec mark range falling to as low as $25 for the microprocessor in a period of a year or 2 years. So not only will we have personal computers or things that we set on a desktop, and you'll certainly find them in universities, which have peak operating speeds in the billion of operations per second range by the end of the decade. You will have in your pocket microprocessors and products, I'm not sure what we'll call them, but which will themselves have performance measured in hundreds of millions of instructions per second, what we associate today with literally the fastest workstations. And so these will enable fundamentally new kinds of products. I have a colleague at Apple, Larry Kessler, who was at Xerox PARC for many years and then came to Apple and worked on the Lisa and then the Macintosh, who wrote an article in Special Issue of Scientific American earlier this year in which he talked about the 4 paradigms of computing. And what Larry was really describing, I think, were these points that I refer to as qualitative change points in the industry. So in his view, or in his system, batch computers characterized in the 1960s, time-sharing computers characterized in the 1970s, personal computers or desktop systems, the 1980s, and in this decade, what Larry refers to as network computers. In each of these eras, the fundamental character of what the computer is used for and how people interact with it is different. So the desktop computers actually brought forth this, or enabled this idea of a graphical user interface, a direct manipulation interface. It was a huge improvement in a number of respects over the previous command line interfaces, in which basically you had to remember a relatively complex, highly structured command language, and we're able to replace that with a set of only semi-structured commands and interactions, which had the net effect of making computing much more accessible to a much broader range of people. You know, if computers were still as hard to use as the early mini computers that we used when I was a graduate student, we would not be measuring the total market size in terms of hundreds of millions of people, but rather in terms of tens of thousands, because it would be limited to universities and scientists and other professionals who would spend the 6 months or 9 months to learn how to use these things. Once again, we are at a point at which we see a major qualitative change possible, and once again, we will see an expansion, a very rapid expansion of the number and kinds of people who will now use computers. We, of course, are very interested in the number of people who will buy personal computers, buy our products, and so we go out and do interviews and surveys on this, and what you find when you do that is roughly 50% of the people that you ask in the United States, 50% of the people say, I haven't bought a personal computer yet, and the large majority of those people will now say, and I have no intention to, because they're either too expensive or they're irrelevant. I don't need whatever they do. I don't need it. I'm doing just fine without them, and I neither, they often say I don't have the skills, but actually embedded in the response, if you actually get down and double click on it, is that they're actually too hard to use. They're inaccessible. So it's quite clear that if we want to dramatically expand the market, we're going to have to do something very, very different in the way of making computing even more accessible, even easier than it is. Now, it may seem silly to people who are in the computer science department who routinely master very complex systems, but believe me, if you watch a few videotapes of naive users, people who have never used a Macintosh, trying to learn what you're talking about when you say Windows, they say a window is something to see through, mice, and so on, it turns out that there are people who literally cannot master these sort of, what turn out to be sort of abstract concepts. So the question is, what are the future systems going to be like? Well, one of the things that's happening is that processing power can be converted almost instantly into improved performance for technologies like speech recognition. We now have recognition technology such that it is possible to create, and in fact people are now creating very large vocabulary connected speech recognition systems. What we don't have yet, of course, is speech understanding. We have very good speech recognition, and with 500 spec marks of performance, you can certainly do a very good job on large vocabulary speech recognition, but we do not have yet good models for ascribing meaning or understanding to that. So once again, we're at the threshold of being able to use and make major use of speech recognition technology. Handwriting is the same thing. You get sort of for the next, probably next couple of years, we will get sort of monotonic improvements in recognition performance, whether we're talking about speech recognition or handwriting recognition, just by turning the microprocessors up faster and faster. We do need, however, major breakthroughs in the technologies associated with speech understanding and knowledge extraction from speech, which we are far from well, relatively far from having. It doesn't mean that speech can't be used in interesting ways, but what it does mean is that we will explore, prior to getting to the pure natural interface where we just talk to your computer, we will have an intermediate step in which we more fully exploit this direct manipulation metaphorical experience of which now in many ways we call virtual reality. So how will we use the new computing power? Well, I think one of the benefits of an electronic presentation is that after I have a conversation with Kleinrock here about pneumatic computing, I can add that in my chart on the fly. But it's quite clear that there are a couple of ways that we will use this computing power. One way is to make computers significantly easier to use, cheaper, and in fact become ubiquitous appliances in the marketplace. Another thing we can do is to use the power to enable significant improvement in the way that we develop software, and in fact in the way that we even think about the platform that we now call or associate with today's personal computers. I will show you an example of a component software system that we're developing at Apple along with IBM and a few other people called OpenDoc, and try to give you a sense of what it's going to mean to software development. You know, in hardware, we've had something like between 7 and 8 orders of magnitude, a factor of 100 million or more improvement in the ability to put transistors on pieces of silicon. I think you'd be hard-pressed to measure more than a factor of 1 order of magnitude, but a factor of 10 in terms of software productivity. Again, that's about to change. Component software systems, object-oriented software systems, which have always had the disadvantage that they were very large and slow in the runtime sense, with the computing power that we now have, the cheapness of memory, now become practical systems to use in consumer commercial products. The other thing, of course, is that once we have the ability to create 500 MIP or 1 billion operation per second desktops, as I mentioned before, we have the ability to create 200 million instruction pocket computers. In fact, we can begin to put computers in our homes. We can begin to replace our analog set-top boxes with computers, and we can begin to produce a variety of products, which actually out of sequence here, a variety of products which we are now beginning to develop at Apple, which go well beyond the personal computer in terms of accessibility to the mass market. One of the reasons that I think component software is going to become very important is that computer applications, software applications have begun to outgrow the marginal utility associated with increasing version numbers. When I first bought a Macintosh, I got Mac Write, which was about an 80K application. When I wrote this little speech, I used Mac Write Pro, which when I looked at the get information, get size thing, it turns out it's a megabyte and a half. It's actually relatively small. If you buy Word, 6 megabytes or more, maybe take 25 megabytes on your disk. I could have just as easily written this with the original Mac Write word processor as Mac Write Pro. Mac Write Pro is a little better, it's a little faster, supports more fonts, and has a few other features, none of which I use in writing up this piece of paper here. So the application has grown by a factor of 20, and the marginal utility has grown by a factor of nothing. So something's got to give, and I think what's going to give is that component software and object-oriented systems are going to replace what is becoming rapidly an unsustainable economic model of computing. If you've ever used a product like ClarisWorks, or Microsoft Works for that matter, you will begin to get an appreciation of what it will feel like to use component-based software. These are applications in which there are actually a series of relatively small applications which are created in such a way that there are consistencies between them. And you can go back and forth from one component to another, spreadsheet, word processing, and so on. The application creators have had to invent the technology for gluing those and maintaining that consistency. What we now have in both Apple, Microsoft, and other people are inventing these middleware, these underlying technologies that allow these components to be glued together in very general ways. With ClarisWorks, you would not have a third party which could create a new component to ClarisWorks. But once you have OpenDoc or something like it, you can do that. You can define an interface to the component technology itself, and third parties can begin to improve or change the individual components in these suites. Now, beyond components are truly object-oriented systems and large complex frameworks like the ones the Intelligent Corporation is using. I think they're farther out for a whole variety of reasons. It's harder to restructure the applications to take advantage of the capabilities. But the net effect of both of these will be significantly more efficient software development, as well as significant changes in the way the software is created and delivered. Today, if I create a change in the platform for the Macintosh, we introduced recently a 3D technology, announced it, we'll introduce it this summer. in order for a user to benefit from that, they have to wait for a third-party application company to make a major revision of, for example, their presentation system, Persuasion in this case, to support that new API, that new software system. With OpenDoc, they don't have to do that, or any of these component technologies, because they're dynamically linkable. All they have to do is to wait for someone to write a small 3D applet, a component, and it will just automatically link into this new suite of existing applications. So there are whole sorts of ramifications of component technology, more efficient software development that will eventually translate into cheaper software development, and more importantly, a speed up in the rate of innovation introduction into the industry. Now what I'd like to do actually is to get my colleague Carl Fligger up and talk a little bit about ubiquitous computing. These are some products that we are now planning in active development. A couple of them we've announced, some of them we haven't. We have an interactive TV system that we have designed, which we are now beginning to use in field trials. We have about 5,000 of these field trials around the world. We have another product you can't see very well called Pippin, which is basically a single application Macintosh that plays a CD-ROM title. The advantage of these for developers is that both of these are Macintosh API compatible. And you'll find many manufacturers doing this, taking advantage of the fact that there are many tools already available for doing things like image processing and creation of multimedia content. All of those things will run automatically on these devices. These devices are not $1,500 devices. They're $500 to $700 devices, going to $350 devices over the next couple of years. You will find similar sorts of things in the area of telephones, whether they're smartphones in the sense of being able to read handwriting, or they're smart or capable phones in the sense of supporting video conferencing. And you probably will see, because of the incredible and growing popularity of the internet, I think that you're very likely to see products which will be made solely to create a window into the world of the internet, the World Wide Web, in the next couple of years, whether made by ourselves or by other people. Now, what I'd like to do is to give you a short demonstration, or actually get Carl actually to give you a short demonstration of the kind of thing that we can now do because we have this new computing capability, much more computing power than we had when we first designed the Macintosh. To give you a sense of how much the computing power has changed in the face of innovation in the industry, the first Power Mac that we brought out a year ago, a little over a year ago, based on the new RISC chip, the 601 that we got from IBM, was 2,200 times more powerful than the original Macintosh introduced nearly a decade, or about a decade prior to that. So more than 3 orders of magnitude in 10 years. And of course, we're going well beyond that over the next couple of years. So, enables a fundamental change, qualitative change in what we can do. Yeah.
So you can lower the lighting One of the things that really made Macintosh accessible by a large body of new users back in 1984 was the idea of real-world metaphors, the ability to take real-life experiences. What is a trash can? What is the file folder? What is the pencil? And apply them to the digital domain. Obviously, we want to get away from this idea of a desktop metaphor. We want to get, as Dave mentioned, more into the world of VR and virtualities as the processing performance increases. So what at first sight looks like a static image on this Macintosh is actually a little virtual environment of one of our engineers' offices back at our R&D headquarters in Cupertino. This is a technology that we've introduced known as Quicktime Vr. It is in some ways quite remarkable in terms of the abilities it brings even to a 68030 based Mac, but it will also allow any of you budding amateur photographers that own 35mm cameras create the kind of digital content you see here. What I'd like to do is start out by turning on the lights. A little more friendly. Let's pause here for a moment. You can notice in the center of this image, I'm going to kind of walk the cursor around it, what appears to be a panoramic photo. Part of Quicktime Vr is an authoring suite that allows you to take 35mm images from a photo CD literally knit them together electronically, stitch them, if you will, in panoramas, which Quicktime Vr in real time adjusts for distortion and perspective that are inherent in the panoramic image. Gee, there's a lot of, I wish I had an office like this. Somebody used that power book. Why don't I see if I can pick it up? This is another usage of Quicktime Vr. Instead of just panoramic views, you can have manipulable objects. So I can pick this up, turn it around, look at it. You notice something interesting is happening in the screen. There's a traditional linear QuickTime movie that's still playing correctly. This is, we've even got within our ATG group a video camera system we call Object Maker that was used to create scenes such as this. Oddly enough, these objects take up quite a bit of storage. That PowerBook, for example, is 500 discrete photographs that are interactively navigated based on input from the mouse. It's about 4 megabytes. This entire panorama, 500 kilobytes, possibly less. In fact, we've done panoramas that are as small as 20 kilobytes. So the ability to put something like that on a storage medium such as today's CD is immense. And if you look at next generation CD formats such as digital video disc, it just gets richer and richer.
Now this is all done, there's no special hardware. This is just a standard Power Mac. It's 80 megahertz Power Mac. So microprocessor now has enough power to do all the pixel manipulation on the fly without any kind of special hardware.
And there are also a lot of very interesting ways you can use Quicktime Vr, because we like to say it puts the reality into VR. Since you can use actual photographs of a site, it's quite easy to go in and show a level of detail that even if you had a high-performance workstation, would still involve fairly significant rendering time. So let's take a look at the White House. We somewhat tongue-in-cheek kind of call this the cruise missile introduction.
We didn't refer to that when we talked to the Secret Service about getting this.
Somehow I have a feeling between now and the final product will soften that a little bit. But we basically landed inside the Blue Room. And I can go in, look around. You've seen me do panoramas before. If any of you are motion sick, watch out. Since these can be cached in memory, you can get extremely high performance. I haven't shown you that you can actually zoom out if you want a more fisheye effect or zoom in. We also took a look at various images that were in the room. We can click on these objects, learn more about them, what have you. The point is, with this kind of technology, though, this is an entirely new medium. I could take a tour of the White House, but it would be shepherded, conducted, very linear from room to room to room to room. We can create what we call multi-node movies, so I can actually walk through a room and look at it from different points of view. Or I could elect to go to a completely new room. And in this case, perhaps I'm entering the main hall in the White House, where I can now look around, look up, look down, really nice floors, but what look I see. Or perhaps if I'm a little bit contrary, maybe I could go back to where I came from because I wasn't done with that. This is what we call a multi-node movie. We have tools, graphical layout tools, that make it very easy for folks that are really computer novices to lay out these kind of multi-node scenes and connections between virtual environments.
Now, let me just point out this point. This is, think of this as an interface, right? And this is a way of actually visiting a virtual space. And we're not really doing anything that requires any kind of manipulation of a symbolic object. We're actually interacting with what appears to the viewer to be a fairly real representation of an actual space. There's no reason, by the way, other than network bandwidth, that this could not be dynamic images, video, that would be captured remotely and available so you could actually set up a camera, be a special camera in this case, but you can set up a camera in the middle of the Champs-Elysees and look at see what was happening this evening in Paris. In fact, you could do that anywhere around the world.
Yeah, of course, this is virtual. Why not just be able to teleport myself? I don't know why they let us photograph this. This is the White House's family dining room, which usually isn't a public tour site. So if you wanted to see where currently the Clintons take their repasts, here it is. But basically, an example of what you could do, say, from an interactive kiosk, or imagine a museum where you could pick up a famous piece of sculpture, manipulate it as an object, or wander around the context of where it was first discovered. Let's go in and do some other things. I showed you a photographic example. It's also important to point out that Quicktime Vr can work with traditional rendered images. This is one of the buildings on the R&D campus, Valley Green 6. which has, even by Apple standards, I'd say one of the more eclectic atrium areas. So here's a rendering, which I can now look around, much as I did the actual scenes of the White House.
If you look carefully, you notice that there was pixel interpolation done on the fly. One of the ways we get high apparent resolution is to actually do subpixel interpolation, again, using the speed of the processor on the fly.
I found the trick to this one is to walk all the way to the green barricade, go off to your corner here. So I don't want to go that way, kind of like this way. Let's go up some stairs. See what that would look like to level up. Of course, the technology of this for gaming is pretty much, I think, self-evident.
But the really significance of it, you don't have to train people to do this. They already know how to do it. You know, it's literally one or two very simple things to do, and they can navigate around this entire scene. Now, this happens to be a synthetic image, of course. You can either use this technology with 3D scenes without the power, computing power necessary to do this with all the polygons in real time.
You know, there are a variety of these, but rather than labor, let me show you something that's very exciting that's purely digital. Apple introduced a couple of weeks ago something called the Quicktime 150, which was actually our second generation digital camera. And we thought it would be fun to go down to a Worldwide Developers Conference and see what we could do with the Quicktime 150. So here are images that did not come from 35mm film, but came from the Sub 1000 digital camera. Obviously, the benefit being no processing costs. Through a high-speed serial link, you download the images directly into the Macintosh, dip them together just as if they were photo CD images. And in essence, you'd have the ability to do this in almost near real time, where you can actually document an event in this fashion, as it was actually occurring. I do want to show you a film example, though, because one of the benefits, obviously, of photographic emulsions is extraordinarily high resolution. I don't know if it's technically accurate, but I somewhat tongue-in-cheek call them write once CCDs. He is acting up a little bit, so maybe we'll ignore him for the time being. But it would be an Apple demo. Actually, I should comment, you know, this has really been, Quicktime Vr, I'm appalled to see that happen. It's really been very stable. I told Dave, you know, my girlfriend won't let me do things with chickens anymore. And I've got a bad case of sunburn, so I think demo test is out of the question. Let me see if VR can help me debug this CPU. Okay, you might say I'll never took you inside like this.
Problem. Let's take a look back here. Yes, yes, see this? Yes, I think this will help. Let me take a listen now. Yes. Yeah, I think that fixed it.
So here's an example of, you know, a living, active sprite. In this case, one of the Quicktime Vr engineers inside of a panorama that we shot with a lipstick camera. If any of you were wondering what Mac this was the old original Mac 2, which was one of the few chassis that were big enough to get even a lipstick. But I think we can probably do even better than that. So let's show you some things that we're currently in the ATG labs and inside of Apple R&D. We expect to be bringing in here to
Future.
Well, here's something like what you saw before. It's a panorama, but you'll notice that as I move around, and I'll do this slowly, we have motion here. So this just isn't a simple, you know, matte, a little bit of blue screening magic. This is an animated moving sprite. In this case, it was derived from video, embedded within inside my virtuality, and as I move around, the right thing happens. Now again, VR in so many cases, the Champs-Élysées, it would be nice to have VR, but you know, kind of appear to be out with the plague if there was nobody there. So we'll soon have the ability to encrust live motion action or other moving objects, perhaps automobiles, what have you, inside of VR panoramas. Finally, sound. This is the Apple company store. If you're ever in Cupertino, I encourage you to, you know, boost our stock price by buying keychains, coffee mugs, baby clothes, things of that nature. But we tend to play a lot of multimedia titles. You can hear sound, but as I pan around, it gets louder or softer. So let's see where this is coming. So the ability to treat sound in these virtual spaces and have it, as the perception research would have shown, do the right thing. Imagine, if you will, a virtual museum where just by walking up to an exhibit, you'd start to hear a narration of it. If you were uninterested, you simply walk away, and the sound goes away with it. So an example of a very natural yet sophisticated UI that requires the user to do almost nothing. It requires the processor to do quite a bit.
Now, obviously, this is not an interface in the sort of general computing interface sense. The point is that you can begin to create not symbolic or abstract computing environments. You can create very realistic ones in which you can completely rely on people knowing how to do the right thing because they've been doing it for their entire lifetime. Now, the next thing I want to show is now you begin to combine some of that with for example, the ability to recognize speech or handwriting, and you can imagine interface designs which are much significantly more easy to use, much more intuitive, and so forth. Now, the next thing I want to do is to give you an example of a small suite, an application that's built using this OpenDoc technology I mentioned. OpenDoc can be thought of as a technology that has really three components. It has an extensible file format, which is self-describing and extensible, so you can keep adding new data types to it. A thing we call bento after the Japanese lunchbox. A set of messaging systems and protocols for allowing the components to communicate with one another. And the third major piece, which is a structure that allows the representation, visual representation, the layout of the components on the screen to be managed in a way that makes sense to the user.
In a moment.
So the individual components are loading. Once the components are loaded, they're dynamically kept in memory and linked into the application as they're used.
May I ask you?
Actually, while Carl is rebooting, I'd be happy to take questions if you have questions. We'll take a minute or two. Thank you. This is alpha quality software.
Were you able to test your theories on sound perception in the water tank with this kind of VR capability?
Well, what I was doing there was trying to apply a fairly simple analytical model to predict what people's perception would be. I don't think there are any good general theories of interface development. Interface is still one of these more of an art than a science sort of endeavors. But I think that the key idea is to take advantage of people's intuitions about how to do tasks. And in fact, Donald Norman, who is one of the Apple Fellows, has this notion that the best interface is no interface. What you would like to do is to basically give people access to the task itself with powerful tools to do what they need to do and not even be aware of the use of any kind of intervening structure or a set of technologies. And we are now beginning to get to the point which we can do exactly that. As you saw, we navigated around the room. We wanted to turn the light on. We turned the light on. You don't have to explain how to do that. You just sort of do what's natural and the appropriate thing happens. Now, again, you combine this completely intuitive, even more intuitive direct manipulation environment with the ability to query in an interesting way, ask the device to do something for you using semi-natural language. You can begin to create interfaces which are both very powerful, very easy, very accessible, and very easy to explain to people. Yes?
There's a competing set of alternatives here, of course. One thinks of Microsoft's OLE 2 and Con and Ba and so forth. And one thinks of your comments earlier about how one can parlay dominance in one area into dominance into another. And so the obvious question is, what gives us hope that you or others will be able, with a technological leap here, of course, to alter that sequence, which of course the folks at Microsoft are presumably running down the road to achieve as well?
Well, I think there are a couple of things. First of all, I mean, I don't want to I don't want to beat up on necessarily. Microsoft has actually introduced a lot of very important things and
It's fun.
very great products.
But it's fun.
The issue is this sort of drive to a single standard going to at some point begin to inhibit technology. One way of looking at this industry dynamic that I showed you before was to say what is going to happen to the aggregate levels of investment in research and development. I made the argument that the hardware side is being increasingly difficult for companies like Compaq to sustain any kind of an R&D program. Obviously, as Microsoft and Intel get more powerful and more profitable, they are investing lots of money in research and development. So it's not exactly as though none is being done. The point is that it's not as diverse as having 50 people do it. So I think the race here is to see if we can create a situation in which smaller people, smaller organizations can continue to innovate. And one of the reasons that the new software technologies are so important is because they reduce dramatically the total cost of developing a new application, for example. So your R&D costs are much less. Therefore, you can, get by and be very successful. A $1 billion a year company and maybe a $10 million a year company. The rate of innovation in the industry is actually, I think, although it's a temporary trough, is about to take a ride up again. And one of the places to look for that is products and technologies being developed in and around the internet. The internet is interesting because although it's a standards-based system and architecture, it's a public standard. No one owns it, and so it's very difficult to parlay the control of a standard into commercial success. And so what you see in effect are the best technologies, the most interesting technologies are winning. So there's a huge and very dramatic amount of innovation taking place in and around the internet. New companies being started. 2 graduate students at Stanford, I'm sure know about them. A little company called Yahoo, which is providing a very simple directory service. How to find your way around the World Wide Web. The venture capitalists are driving these guys nuts, trying to give them money. And, a year ago, they were graduate students in a department very much like this one. So whether you consider that a good thing or not a good thing, I'm not sure, but certainly there's a lot of opportunity.
Working? I think we're working. Okay, from a user point of view, there's technologies such as Bento, as a file format to store rich data types and messaging architectures and user experience in handles. Presents to the user with the notion of a document in which you can invent things. And since we want to take computing to a little bit higher level, maybe these just shouldn't look like traditional blank windows. Maybe we could make them more like a notepad, or since we're in the engineering school, more of a grid. Although most of the press that's in LA right now is probably running on legal pads. The idea here, though, is this opened up part, which I've treated from the user-centric point of view like a piece of stationery, can now act as a container into which I can embed other parts. Case in point, most of us work with text in some way, shape, or form. So let's go ahead and just drag and drop, which is a Macintosh technology that's used extensively by OpenDoc, a text part into the document. And of course, I could do traditional things like resize the area. I could go also and drag in a graphics part. Without right here. Resize it a little bit as well. And these are basically faceless engines. I have a text processing engine and a graphics engine. Let me go ahead and type something here. But if I wanted to see what was actually going on and kind of drop into this messaging architecture, I've got an interesting part that probably wouldn't be of much interest to end users, but to those of us here. First rule of this OpenDoc demo is deactivate objects before we drag it in. Something we call the inspector. And the inspector will basically just keep an eye on what's going on and keep track of the parts that the messages, the various OpenDoc parts, send back and forth. So for example, if I click on the container part, it tells the inspector, I've been told to act like legal paper. Or if I click on some text here, I can see the current font size or the current attribute. Maybe I'd like to make that larger. It's 24 point. Maybe I'd like to take that and make it bold, what have you. So, this is a user interface of a sort, if you will. This is kind of analogous to a network, student. Just lets me see the traffic going on. However, most of us would probably rather build a little more sophisticated interface to work with. So here's an interesting part, what I call Folio. You can think of this as a kind of roll your own toolbar or roll your own palette. And if I want to go and work with some graphics, I can also, courtesy of OpenDoc, bring in graphics primitives. These are just very simple little parts that, for example, know how to draw rectangles, or know how to draw an oval, or adjust fill colors, since I have literally tens of thousands to choose from, or perhaps the width of the drawing pen. Now, again, these become associated with this container document. So if I were to get tired of this, need to go off and do something else, the next time I open this up, it would remember the associated screening tools and open them up at the same time. So if I activate my drawing area, I can now click on one of these, draw a rectangle, and choose a fill color for it. Let's adjust the pen width. I'll go in and draw something else, in this case, an oval. Perhaps add some fill color to that as well. But if I'm a graphics specialist, maybe I like to do a lot of work with Bezier curves, I could build a custom Bezier curve palette. If I'm more of a bitmap editor, the magnifying glasses, the pencils, the erasers, you can literally build exactly the graphics you want if you need it. We talked a moment ago, Dave mentioned some of the newer technologies from Apple, such as Quickdraw 3D. In the past, it's taken a while for developers to support these, primarily because they've had these sprawling monolithic applications. They've had a couple hundred engineers more concerned about how to add better footers, perhaps in support of some of our newer APIs. So here's an example of an OpenDoc part that supports Quickdraw 3D. And I'll drag and drop this into our document. Let's resize it a little bit as well. Hide the controls since I don't really need them. And let's take a document that's in our Quickdraw 3D metafile format and embed it inside of this part, which is in turn embedded inside my document. And yes, it does the right thing. Now, Quickdraw 3D is a technology that really wasn't around when this virtual suite was defined architecturally. And one of the benefits, obviously, of object-oriented technology would be, say, the concept of polymorphism, where I should be able, perhaps, to go back to here, choose a fill color for something that was designed to work with a simple 2D primitive, and it works. So OpenDoc can also be a vehicle by which Apple, or for that matter, others such as Nagel and IBM that are supporting us on OpenDoc, can more rapidly deliver innovations in middleware to end users, which is one possible way to stick a lever, if you will, inside that layer chart and start to cause a few things to crack. But so far, the interfaces you've seen are all fairly adult, somewhat business-like. What if I wanted to take these same engines, my 3D engine, my text engine, my graphics engine, and sell it to an entirely new market? This is more of an academic interest, given our share at K-12. So let me go in and show you a part that simply implements a user interface, appropriately called the bear, for reasons that you'll see in a moment. Here's my friend the bear. Let me activate the graphics, and maybe I'd like to change the fill color of that particular rectangle. Click on the rectangle. Maybe I'd like to change the line. Just to show you that I do mean what I say. It's 3D too. And of course, if I like, I can play a little game of Simon Says if I box him on the nose. I'll spare you that. Oh, no, I'm about to show you something really cool anyway. There's also the issue of localization. You can target a specific market, but how do you take software that was written by people who speak English, or English-speaking culture, and, if you will, localize it? Well, the traditional approach to this has just been to take your menus, your dialog boxes, what have you, and translate them into the language. This has been a passable approach, say, for the US and Western Europe, and quite a few countries that share languages that use the Roman alphabet. that have a somewhat similar cultural or heritage background. But what if, on the other hand, you wanted to get into some of the very rapidly growing emerging markets, such as the Far East, in addition to Japan, which is almost exponentiating, Korea, India, a variety of them. Wouldn't it be nice if you could write an interface that reflected true cultural diversity? For example, a culture that was much more ornamental in terms of its interpretation or worldview, perhaps, than our own. Remember first rule, remember big parts. So here, I won't have to worry about that when the OpenDoc is actually done. Please bear in mind, not only am I showing you a pre-release technology, I'm doing SQ&A testing via OpenDoc. I don't think our own SQ&A labs have done yet. So here's a Hindi part, which if I drop, will give us an interface. It is not only localized in terms of language, it's localized in terms of culture. And if I, for example, wanted to adjust the pen thickness, or perhaps just the fill, or add something entirely new to this document, I could in fact do that.
So notice a couple of things. First of all, we just constructed a very simple application right before your eyes using components. And in fact, in this case, these are components written by people that didn't necessarily talk to each other during the process of creating components, but nonetheless, they all work together. Second thing is you can begin to see, we can begin to get away from this idea of a word processor, for example, and more into the concept of something, again, that people already know how to use, which is a piece of paper and tools to create marks, create symbols on that piece of paper. And then the third idea is that if you construct your application in the right way, that is, you separate the user interface features from the engines which do the basic text or graphic manipulation, you can basically, again, with other component technologies, localize or create other versions designed for different age groups or different market segments or whatever, very easily and obviously very, very rapid. I think I'll stop at this point. I think what I've hoped that I've gotten across to you is the idea that the progress of basic technologies of computing have brought us to the point at which we can create yet another major qualitative change in the whole experience of computing as well as the systems for developing software.